Hello, this is Algebra 2, Chapter 2, Section 7, Parent Functions and Transformations. And I will say that coming from 2.6, which was, I think, kind of difficult, this section is actually a little bit of an easy section, so hopefully that'll kind of give you some relief. Anywho, so this is parent functions. So basically, parent functions, it kind of talks about families of functions. So I'm kind of going to give you here four functions that we have in math, and there are definitely others, but for now we're going to start with these four, and we're going to give you some characteristics of these functions. And basically what I want you to understand by the word parent is that just like oftentimes children resemble certain traits from their parents, and certain families resemble certain traits, like for example in my family we all kind of have the same large noses. But anyway, so you can usually tell an Olmeda from anybody else by looking at their nose. And now don't be staring at my nose. But anyway, so in a similar way, all of these families of functions are kind of like that, where they all have specific traits and characteristics. They can change. Obviously, they won't all be identical. They can change, but they will have some traits that are all the same. And we've kind of touched on some of this already in the past, especially as it relates to absolute value. But first of all, I want to start off with two types of functions that we consider linear functions, meaning that they look like lines. But the first one is a constant function. And a constant function pretty much always, I mean, yes, it's a line, and so is that. They're both lines. But a constant function will always be a horizontal line, kind of like going along the horizon there, a horizontal line. And whereas the identity function is a line that has a slope to it. And so they are both lines, but they are different kinds of lines. So they're like cousins, so to speak. But anywho, so I wanted to tell you that the equation of a constant function will always be y equals, or f of x equals a. A is just there to represent some number. We don't know what this number is because there's no scale here. But let's say that that was a 1, then it would be y equals 1. If that was a 5, then it would be y equals 5. Or it could be f of x equals 5. But it's always going to equal a number. The domain of a constant function is on the all reals. We talked about going along the x-axis, and you'll always be able to find a value when you go up or down. So the domain of a horizontal function is always going to be all reals. And in fact, the domain for all of these functions is going to be all reals. But the range, however, what are the possible y values? Well, because you can see here from the graph, there's only one y value, which is the a. So for the range of the function is going to be the same as the actual function itself. If this is a 5, then the only value you're going to get for y is y equals 5. There aren't going to be any other values here or above. So that's the constant function for you. Then you have the identity function, which is y equals x, or f of x equals x. And in this case, domain is again all reals, but so is the range, because it goes forever in both directions, positive and negative. So your identity function is there. Absolute value is unique because it looks like a v. So definitely have a shape of a v for the absolute value function. This is what the function looks like, or the equation anyway. Domain, we talked about this before, all reals, but in this case the range, because it starts at 0 and goes above, there's no y values below, y greater than or equal to 0. And then of course our quadratic, anything in the form of x squared, is going to look like a parabola, like a U-shaped graph. And like the absolute value, they will have the same domain, all reals, but the range, the y values are only from 0 and on up. I just want to be clear that this is just the parent graph. This means that any graph that has x squared in it, like if I shouldn't say that has x squared in it, but any graph that has x squared as its highest exponent, for example, if I pick y equals x cubed plus 5x squared, this graph will not look like a quadratic because the x cubed is bigger than the x squared. So I don't want to confuse you, but any graph that has like y equals x squared plus 5x minus 7, in this case, of the three terms that this function has, the x squared is the highest exponent. So any function that has x squared as the highest exponent is going to look like a u. Any graph that has absolute value bars in it is going to look like a v. And of course, any graph that has x as the highest exponent is going to look like a line. And any graph that doesn't have x in it and only has like y equals a number is always going to look like a horizontal line. So that being said, the second part of the lesson today is transformations, which is what happens when you start adding different numbers to these functions. So the first thing we're going to do here is identify the type of function represented by each graph is what it's asking us to do here. So this shouldn't be too complicated. We look at A and we can see that it has a shape of a V, and so therefore this one is an absolute value function. Very nice. We look at B, and because it looks like a horizontal line, this is a constant function. All right? So, like I said before, it's not a very complicated section, but there you go. So now your first do-it-yourself. Look at these two graphs and determine what type of function is represented. So the same directions as the example. And then we'll go on to what I was talking about earlier about the transformations. We have a couple of different types of transformations. The first is what we call a translation, and we have vertical translations and horizontal translations. So this is a generic way for you to remember what it looks like, but I just want to remind you that this is the case for absolute values and quadratics, and even beyond. As the year progresses and we learn new functions, this will always be true. So basically, for example, you have y equals x squared is the parent graph. You could also have y equals x squared plus 3, or y equals x squared minus 5. So these are all from the same family of y equals x squared. And so what we're saying here, you could even have y equals absolute value of x plus 2. Something like that, okay? So what I want you guys to get from this is that you have the function itself, which is either the x squared or the absolute value. That's the parent graph. So when it says f of x, this is referring to the parent graph. And so if you see the parent graph in your equation, and then it has an extra plus or minus something, like here's my parent graph, x squared, parent graph, x squared, and then it's a plus 3, a minus 5, or a plus 2, what that tells you is that the graph is going to move k units up if the k is positive, or k units down if the k is negative. And we'll show you an example in a second of how that works. So just want to be clear that for the vertical translation, it's going to move up or down, and it's going to go up if it's positive, down if it's negative. So this graph right here is going to be the exact same graph as x squared, but it's going to be moved, it's going to be shifted, so to speak, 3 units up because of the plus 3. This second graph is going to be the exact same thing as x squared, but it's going to be moved 5 units down because of the minus 5. And this guy, because the parent graph is absolute value of x, this graph will look exactly like the absolute value function, but 2 units up. Okay, and so then we have, oops, let's get my eraser going here. Then we have the same scenario for this guy. And what you'll notice here is that here we have a plus or minus k that comes after the function. In this case, the plus or minus h is inside the function. So for a horizontal translation, the plus or minus number comes inside the translation. So, for example, instead of having y equals x squared plus 2, it would be x plus 2 squared. The plus 2 would be inside the function. For the absolute value, it would be like x minus 1, for example. So the plus or minus won't come after the absolute value or after the x squared. It'll be inside the actual grouping symbols. In this case, the grouping symbol being parentheses. In this case, the grouping symbol being the bars. But again, if it's a plus h, like a plus 2, that means you're going to shift 2 units to the left. A plus h shifts it to the left side. Negative h, like negative 1, is going to shift it to the right side. All right? So now what we'll do is I'll give you an example so you can kind of see how that works. So here we go. Example 2 says, describe the translation in y equals absolute value of x plus 2. And the first thing I want to do is graph the absolute value of x. This is the parent graph. And so this is for my little friend, Miss Feisty over there. I'm going to choose whichever x values I want. I'm going to pick -1, 0, and 1, because I can do that. And then when I plug -1 into this absolute value, the absolute value of -1 is +1, and 1 plus 2 is 3. The absolute value of 0 is 0 plus 2 is 2, and then again we get 3 here. So when I graph this function, it's going to look like negative 1, 1, 2, 3. I am so sorry. Oh well, I'm just going to keep going. 0 and 2, and 1 and 3. 1, 2, 3. I'm saying I'm sorry because I actually did not graph y equals, when I plugged in the values, I plugged them into this. So what I'm graphing here is y equals absolute value of x plus 2. Okay, and that's not what I wanted to do, but I'm going to now graph it over here. What would y equals absolute value of x actually look like? I could still pick the same numbers, but the absolute, I'm supposed to plug negative 1 into this. And earlier I plugged negative 1 into this, which is why I got these weird numbers over here. So I kind of fixed that over here. I made this a plus 2. So what I actually graphed, the orange graph, is actually the translation already moved. And I didn't want to do it in that order, but I did want to graph both of them. So when I plug negative 1 into the absolute value of x, the absolute value of negative 1 is positive 1. The absolute value of 0 is 0, and the absolute value of positive 1 is positive 1. So when I graph that, I get negative 1, 1, 0, 0, and 1, 1. Okay? Now the idea here is that eventually you won't actually have to graph it this way. But what I wanted to show you is how what we said earlier works. What you will notice, this is the blue graph is the actual parent graph, y equals absolute value of x. That's the parent. And what I'm doing is the 3 points that I've picked, like I said before, because it's a plus 2, each of those 3 points is going to move up 2 units. So this point has a y value of 1, and when I go up 1, up 2, now this point, which is the translated graph, has a value of 3 for the y, which is basically 2 more than the 1. Say you have a 0. It's at a 0, it goes up 1, goes up 2, goes up 1, goes up 2. So all the points basically just shift 2 units up, and that's how you can graph these functions very easily, if you know what the parent graph looks like. So these are the graphs that I want you to try. Keep in mind that this guy here is a vertical translation. The minus 4 comes after the x squared. But this one is inside the bars, so this is going to be a horizontal translation. So horizontal for A and vertical for B. Also, with transformations, we have what they call a reflection. And again, we've talked about this in some of our homework, where the absolute value was negative in front. So basically, if there's a negative in front of the function, so that would look like negative x squared or negative absolute value of x, then that means that it flips over, it's a reflection, a mirror image if you will, on the x-axis. So our v that looks like this normally would flip over like this. It would flip on the x-axis. Whereas the other option, the f of negative x over here, is a y-axis reflection, which means if the negative was inside the bars, like a negative x here, okay, or a negative x inside the parentheses like that, then that would mean that it would flip. If your v is normally like this, then it would flip on the y-axis. So this doesn't really make much sense, but let's say that you had a graph that looked like this, then it would flip like that. Now, I will say that the latter, this y-axis reflection, doesn't happen very often. The one that you're going to see the most, especially in your homework today, is the x-axis reflection with the negative in front. So we'll see how that works out here. Describe the reflection of y equals negative x squared, then graph the function. Again, I want to start by graphing the parent graph, and this time I'll do it the right way, because I don't want to be crazy. X, y, negative 1, 0, 1. I can pick whatever numbers I want. So I'm going to graph y equals x squared. That's the parent graph. So when I take negative 1 times negative 1, I get positive 1. 0 times 0 is 0, and 1 times 1 is 1. And of course, x squared means times it by itself. So I can get negative 1, 1, 0, 0, and 1, 1. And I have a parabola, like that, okay? But now when I graph y equals negative x squared, negative 1, 0, 1. What this is telling me to do is to take negative 1 times negative 1, which is positive 1, and then times it by a negative, which will be negative 1. 0 times 0 is still going to be 0 times a negative is still 0, but 1 times 1 is positive 1 squared, but 1 times negative 1 will give me a negative. So now when I graph that, it'll be -1, -1. There's still 0, 0, and 1, -1. And you will get the exact same graph, but flipped upside down right along the x-axis. That's what we mean by mirror image. Okay? So this is going to have an x-axis reflection. And then we've already graphed the function. So now you can try these. And then we will go on to our last example and our last type of transformation, which is what we call a dilation. A dilation either shrinks or enlarges a figure proportionally. So when you have a nonlinear function that's multiplied by a non-zero number, so if it's multiplied by a zero, it doesn't even count, then the function is either stretched or compressed vertically. And so like before with the whole H and K thing, I want to give you guys some basis for when is it a stretch and when is it a compression. So if the coefficient, and that's the number in front of the function, so if the coefficient is bigger than 1, then it's going to stretch it vertically. If the coefficient is between 0 and 1, which basically means it's like a fraction, like 0.3 or 1/2, 1/3, 3/4, any number that's between 0 and 1 is going to compress it vertically. Okay, so we're going to try an example with the dilation, and it says describe the dilation of y equals 4x. Because 4 is greater than 1, then we know that it's going to stretch it vertically. So what we're going to say, because that's to describe the dilation. So the graph of y equals 4x, it's going to be, what did I say here? Stretched vertically by a factor of 4. What that means for our graph is that it's going to have a very much steeper slope. This is a very easy graph a function to graph. First of all, I want to graph for you the parent graph, which is y equals x. And I'm not going to make a t-table because I think that y equals x is an easy graph that we can graph with y equals mx plus b. So it's going to be plus 0. So my y-intercept is going to be 0. And my slope is going to be 1. So up 1 over 1. Up 1 over 1. And so, oops, that was a lot of deletion there that I wasn't looking for. But anywho, so I'm going to do y equals x. It's going to look kind of like this. That's the y equals x graph. That's the parent graph. And the dilation is going to be stretched vertically. So it's going to be like we're stretching it out. Okay, like if you were going to stretch this graph out, and what that's going to do is going to make it have a much steeper slope. And again, graphing y equals 4x is going to be pretty simple because it's also in y equals mx plus b. And it's also plus 0, so it's also going to have a y-intercept right here at 0. And then the slope is now 4, so it'll be up 1, up 2, up 3, up 4, and over 1. And so that graph is going to look like this. And you can see how it got stretched and pulled tighter to the y-axis. So that is, but again, the description there is that it's stretched vertically by a factor of 4. And then we've graphed the function. So now I'm going to have you guys try this little guy. And once you've done those two, then we can call it a day. That means that you've done your notes for the day. I'll see you in class tomorrow. And thank you for watching.